Lesson 4 on quotient rule. You should know the power rule and product rule, so make sure you've watched those videos if you haven't yet. And now we're going to learn the quotient rule for differentiation. The quotient rule, simply put, is if we have a function that is a quotient of two functions, we can find the derivative of that function by doing the derivative of the function in the numerator times the function in the denominator minus the derivative of the function in the denominator times the function in the numerator. And that all gets divided by the function in the denominator squared. If you want a proof of that rule that I just showed you, make sure you click the link at the top of this video right now. And the rest of this video is going to be dedicated to actually practicing some examples where we're going to need to differentiate a function using the quotient rule. So I'll leave the quotient rule up at the bottom of the screen for you here so you can reference that as I differentiate these functions. And let's start practicing it. Let's do a few practices of finding the derivative of a quotient of two functions. So function f of x is a quotient of a linear function and a quadratic function. Let's differentiate f of x. So let's find f prime of x. Now when we find the derivative of f of x, if we follow the quotient rule, it tells us to do the derivative of the function in the numerator. So I'm just going to call that the derivative of the top. So the derivative of the top would just be 3. Multiply that by the bottom function, x squared plus 5, minus, then I do the derivative of the bottom function. So the derivative of x squared plus 5 is 2x. Multiply that by the top function, 3x minus 4. And then that all gets divided by the bottom function, x squared plus 5, squared. Don't forget to square the bottom function. So that is the derivative. We just have to simplify it. So keep in mind the numerator is not in factored form right now. I can tell that because of this minus sign. So we cannot start canceling any factors because the numerator is not in factored form. So what we do is we expand it out, collect any like terms, then see if we can get it back into factored form. So let's expand out the numerator of our derivative. So let's distribute the 3 and the negative 2x. When I do that, I would get 3x squared plus 15 minus 6x squared plus 8x. And that's all over. Now I'm not going to expand the denominator. The denominator is already in fully factored form, so I'm going to leave the denominator the way it is. And then in the numerator, check for any like terms. I have one pair of like terms, the 3x squared and the negative 6x squared. I can collect those together and get negative 3x squared. So I have negative 3x squared plus 8x plus 15 all over that function in the denominator, x squared plus 5 squared. And what I would do here, now this is actually my final answer. It doesn't simplify any further. The numerator doesn't factor. But what I would do, I would try and factor it. It's a quadratic. You would check and see, does it factor? So you would look and see, are there any numbers that have a product of negative 45 and a sum of 8? Now, if this function is factorable, there will be numbers that satisfy this product and sum. How can you be sure that there aren't numbers that satisfy this product and sum? I mean, 15 and negative 3 aren't going to work. 9 and negative 5 aren't going to work. There are no numbers that satisfy the product and sum. But let's say maybe you're not sure. Maybe you think there are numbers, you just can't think of them. How do you check? You can check the discriminant. Check b squared minus 4ac. If b squared minus 4ac is a perfect square number, like 4, 16, 25, 36, 49, so on. If you get a perfect square number, that tells you that the quadratic is factorable because it would have rational zeros. If you get a non-perfect square number, it tells you the quadratic is not factorable. So if you got like 10, 11, 12, or negative anything, that would tell you that it is not factorable. Now, I'm not talking about how many zeros it has. That's usually what you use the discriminant for. What I'm talking about is checking to see if it's factorable. And that's solely based on whether the discriminant is a perfect square number or not. So if we check the discriminant, 8 squared minus 4 times negative 3 times 15, I would get 64 plus 180. That's 244. Now, 244 is not a perfect square number. If I tried to square root it, I would get an irrational answer. Let me prove that to you. So let me square root 244. See, I get an irrational answer. That tells me that 244 is not a perfect square number, which means that the quadratic is not factorable, which means that This is my final answer. Before I move on to example B, let me just make sure you fully understand how I set up this first line. If you can set up that first line, then the rest of the question, the simplifying part, just requires like grade 9 and 10 skills. So how did I set this up? Well, this 3, that 3 is the derivative with respect to x of the top function. So it's the derivative of 3x minus 4. That's where that 3 came from. And then the x squared plus 5 is just the bottom function. Where did this 2x come from? That 2x is the derivative with respect to x of the bottom function of the x squared plus 5 function. And then this 3x minus 4 is just the top function. And then all over the bottom function squared. So sometimes if you look at a solution, you may see your initial line having this Leibniz notation involved in it. You may actually see this notation. This means the derivative with respect to x of 3x minus 4. Now, I just actually wrote what the derivative was. I just wrote 3. But I suppose we could have written this as our first line, communicating what we were actually going to do. But I just went ahead and did the derivatives. Let's try a couple more examples. Let's find the derivative of this g at x function. And this g at x function is a quotient of two functions, so we can do quotient rule. So if I want to do the derivative of g at x, I would do the derivative of the top. So the derivative of 6x minus 5 is 6. Multiply that by the bottom, minus the derivative of the bottom, which is 3x squared, times the top. And this all needs to be divided by the bottom function, x cubed plus 4 squared. Don't forget the squared. And now I need to simplify this. The numerator is not in factored form, so don't try and cancel anything. What I'm going to do is I'm going to expand it out and then see if it factors further. So let's go ahead and try that. So g prime of x equals, let's expand the 6. My standard form in the numerator would be 6x cubed plus 24 minus 18x cubed plus 15x squared. And this is all over x cubed plus 4 squared. G prime of x equals, let's collect any like terms we have. I just have one pair of like terms again. 6x cubed minus 18x cubed. I can collect those together and get negative 12x cubed plus 15x squared plus 24. All over x cubed plus 4 squared. And like I said, we never expand the denominator. Okay, the numerator, I think all I could do with the numerator, I could common factor out a 3. I mean, I don't think that's going to help us simplify anything. So I would accept this as a final answer. But if you wanted to, you're more than welcome to common factor out a 3, or a negative 3 even. When the first term, the leading coefficient, is negative, I like to common factor out a negative. So I would take out a negative 3. And that would give me 4x cubed minus 5x squared minus 8 all over x cubed plus 4 squared. So I would take either of those two answers. Either are acceptable. Let's try a third one. This h at x function is once again a quotient of two functions, so to find the derivative, I'll use the quotient rule. Derivative of top is 2 times the bottom function. Now I'm actually going to write this root x. That root x means x to the half, so I'm going to write it like that. Minus the derivative of the bottom function, and like I said, this root x is x to the half, so when I do the derivative of it using the power rule, I will get a half x to the negative a half, and that needs to be multiplied by the top function, 2x plus 8. And this is all over the bottom function, root x, which I'll write as x to the half, squared. Okay, we need to do some simplifying here. So for this one, I'm actually going to notice that the two terms I have, and I should mention there's two terms, right, because they're separated by this minus. Here's my first term, and here's my second term. Those two terms both have a factor of x. This one has an x to the half, this one has an x to the negative a half. So I'm going to common factor out from those two terms the power of x that has the smaller exponent. So I'm going to common factor out an x to the negative a half. I'm actually going to common factor out this half as well. Now I need to divide both of those terms by this half x to the negative a half that I took out. So I have to divide this by a half x to the negative a half. Well, 2 divided by a half is 4. And x to the half divided by x to the negative a half, I would keep the x and subtract the exponents. A half minus negative a half, that's a half plus a half, which is 1. So 4x. That worked out nicely. Minus, now I need to divide this term by what I took out. Well, I took out this factor of a half and the factor of x to the negative a half. So those are both gone, and I just have 2x plus 8. Make sure you put it in brackets to know that we are subtracting both the 2x and the 8. And this is all over. And I have a power of a power in the denominator, so that means multiply the exponents. A half times 2 is 1. So in the denominator, I just have x. Now, a couple of things I can do to simplify here. I will subtract both of those terms and then simplify inside those square brackets by collecting like terms. But also, I've got this factor of a half. What I can do with that is just leave the 1 there, and the 2 is actually can be just moved to the denominator. And I can take this power of x to the negative a half, and I can move that power to the denominator, and what that does is it changes the sign of the exponent. H prime of x equals, this 1 will stay in the numerator, but I don't have to write it. This x to the negative a half is moving to the denominator. This 2 is moving to the denominator. And all I've left in the numerator is 4x minus 2x minus 8. So that would be 2x minus 8. And that's all over this 2. And then an x to the half and an x. And I can collect those powers of x together using my exponent rules. I know that when powers of x are being multiplied, I can keep the base and add the exponents. Numerator, I'm also going to write in factored form. Divide 2 out from both of the terms, and you'll see why I did that in a second. 2, and then add the exponents, a half plus 1. So 1 over 2 plus 2 over 2 is 3 over 2. So I have x to the 3 over 2. See why I common factored out the 2? 2 divided by 2 is 1. Those cancel. And my final answer for h prime of x is equal to x minus 4 over x to the 3 over 2. There's my final answer for the derivative. That one simplified nicely. Part D, actually we need something called the chain rule in combination with the quotient rule. Now, if you're in my class, we won't learn the chain rule until next lesson. But this is a good, maybe just preview of what we're going to be using in the future. So this function r at x is a quotient of two functions. So we can find the derivative of r at x, so r prime of x, by doing the derivative of the numerator. So the derivative of the top is actually just 1, that's nice, times the function in the denominator. And I'm going to rewrite that radical sign as a rational exponent. I'm going to rewrite it as an exponent of a half minus the derivative of the bottom function. Now, let me just show you off to the side. When I find the derivative with respect to x of this x squared minus 1 to the half function, I actually have to use something called the chain rule, because what I have is kind of a function of a function. I do the derivative of the outside function with respect to the inside function. So you'd use power rule like normal. You'd bring the exponent down, write it as the coefficient of the base of the power, reduce the exponent by 1. But then that needs to be multiplied by the derivative of the inside function, the derivative of the base of the power. Like the base of the power we consider our inside function. The base of the power is x squared minus 1. The derivative of that is 2x. And then this actually simplifies because we've got a 2 divided by 2, that's 1. So it's equal to just x times x squared minus 1 to the negative a half. So this is the derivative of the bottom function. So I'm going to put that right here. So minus x times x squared minus 1 to the negative a half. And that needs to be multiplied by the function in the numerator. And all of this is divided by the bottom function squared. So the x squared minus 1 to the half needs to be squared. All right, now we just have to simplify this. So let's look in the numerator. It's not in factored form. So what we want to do is we either want to expand it, which we can't do because of these rational exponents. So what we're going to do instead is we're going to check is there anything that common factors out. And yes, notice both terms, this term and this term, both have a factor of x squared minus 1. So we common factor out the one with the smaller exponent. So we common factor out that one. So r prime of x equals, let's common factor out an x squared minus 1 to the negative a half from both terms. When I divide this term by x squared minus 1 to the negative a half, I know my exponent rules tell me to keep the base and subtract the exponents. A half minus negative a half is 1. Minus. Now let's divide this term by what we're common factoring out. The x will still be there. The x plus 3 will still be there. However, this x squared minus 1 to the negative a half is being divided out, so that one is gone. And this is all over x squared minus 1 to the half to the 2. I can multiply those exponents and get 1. So it's all over x squared minus 1. And now let's look in those square brackets. Is there anything I can simplify? Oh, and also, this power has a negative exponent. I'm going to bring it to the denominator so that the exponent becomes positive. And then also, I'll be able to collect it with this power because they have the same base. So in the numerator, all I'm going to have left is this x squared minus 1 minus x times x, which is x squared, minus x times 3, so minus 3x. All over the x squared minus 1 to the power of positive a half, so this power that I brought down, times this x squared minus 1 that's to the power of 1. One more line left. The derivative equals, collect our like terms, x squared minus x squared, those are gone. I've got a negative 3x minus 1. All over x squared minus 1. Since those are powers with the same base being multiplied, I keep the base, add the exponents. 1 over 2 plus 2 over 2 is 3 over 2. And there's my final answer for the derivative. Let's do 2 application questions now. So example 2 says, determine an equation for the tangent to this curve, and I've just given you a graph of that curve at x equals 2. So let me just make sure you understand what we're trying to find. When x equals 2, if I were to draw a tangent to that function, so a line that just touches that function at one spot, and I'll draw my best tangent line I can right here, just touches the function at that one spot. Now that's not a perfect tangent line. What will be the equation of that line? So if we want the equation of a line, we need to know its slope and y-intercept. Let me just show you in Desmos a better graph of this tangent line. So I have Desmos graphing the original function in red, and then also a tangent line at any point I want. We want it when x is 2. So let me move this point over to when x is 2. We want the equation of that blue line. So I'm going to need to know the slope of that blue line. And the slope of a tangent line, that's what the equation of a derivative tells us. So we would just plug 2 into the equation of the derivative, which I have Desmos doing for me here, and we'll get 1.44. So we know the slope of it. And then we'll also need to know the y-intercept. So we're going to need to know this point down here, which is apparently negative 2.556. How are we going to calculate that? Well, if we know the slope of a line, and we know a point on the line, we could solve for the y-intercept. We could solve for b. Well, what point is on the tangent line? Well, we know the tangent line touches the original function when x is 2. So if we figure out where the original function is when x is 2, which I have Desmos doing for me here, plug 2 into the original function, it gives me a third. So if we know a point, the slope, we can solve for the y-intercept and write the equation. Let's do that. So let's start by finding the slope of the tangent line. If I want the slope of the tangent line, I would have to plug 2 into the equation of the derivative. So I need to find the equation of the derivative for this function. I need to find y prime. Y prime equals, I do the derivative of the top, so 2x, times the bottom, minus the derivative of the bottom, which would just be negative 1, times the top all over the bottom squared. Now, since I'm just interested in the value of the derivative when x is 2, I don't have to simplify this. I could expand it out, collect my like terms, get it in a simpler form, but since I'm just interested in the value of this when x is 2, I could right now just plug in y prime at 2 and evaluate it. It's up to you whether you simplify first or not. So I've got 2 times 2 times 5 minus 2 minus negative 1 times 2 squared minus 3 all over 5 minus 2 squared. So I have 4 times 3, that's 12, plus 1 times 1, so that's just plus 1 over 9. So I've got 13 over 9. Y prime at 2 equals 13 over 9. And let me just show you 13 over 9 is that approximate value 1.44 that Desmos was giving us. So we have the slope of that black tangent line there. If I want to write the equation, I also need to know its y-intercept. And to find the y-intercept, I'm going to have to know a point on the tangent line. And I know that the original function and the tangent line share this point right here when x is 2. So to find a point on the tangent line, I plug 2 into the original function. I'll evaluate the original function when x is 2. It would equal 2 squared minus 3 over 5 minus 2. That gives me 1 over 3, a third. Okay, so I have a point. The point 2, a third, is where the tangent line touches the original function. So that's my xy value. I have the slope of the tangent line. That's my m value. So now I can write the equation if I solve for b using those 3 pieces of information. Now let's find, I'll do it over here, equation of tangent line. So these questions are always in 3 parts. Equation of tangent line. The equation is always going to be in the format y equals mx plus b. Sub in the y value of the point, sub in the slope, sub in the x value of the point, and solve for b. So we have a third equals 26 over 9 plus b. Isolate for b, and we'll leave our answer as a fraction. I'm going to get a common denominator at this step as well, so that 1/3 I'm going to change to 3 over 9. Subtract this 26 over 9 to the other side, and my b value is going to be equal to negative 23 over 9. So let's write our final equation. Our final answer would be y equals 13 over 9x minus 23 over 9. That is the equation of the tangent line at an x value of 2. Last example. This question says determine the coordinates of each point, that implies maybe there's more than one, on the graph of this h at x function where the tangent is horizontal. So a horizontal tangent has a slope of 0. So this is a complicated way of saying when is the derivative of this function? When is h prime of x equal to 0? For what value of x is the derivative 0? That's what we're looking for. Let me just show you that in Desmos. So I have Desmos telling me the value of the derivative of any x value I want for this original function here that's in red. We're looking for when is that derivative equal to 0? Well, notice, pay attention to these numbers here. When are those numbers 0? Those numbers are 0. It looks like right around, getting really close to 0. Oh, I saw it right there. At one spot when x is 4. X value of 4 that has a horizontal tangent. If I plugged 4 into the equation of the derivative, I get 0, which implies there is a horizontal tangent there. So how are we going to figure that out algebraically? Well, we need the equation of the derivative. I think this is a function we already differentiated earlier in the lesson. Yeah, it's part C right here. We already differentiated that function. This is the derivative. H prime of x equals x minus 4 over x to the 3 over 2. Let me just copy and paste that over. We already have the derivative. So I'm interested in when is this equal to 0? For what value of x does this derivative become 0? So I just set this to 0 and solve. Now, what makes a fraction become 0? If the numerator is 0. So you can, algebraically, you can multiply both sides by this denominator, and then it disappears. And we get 0 equals x minus 4, and we get x equals 4. If I plugged 4 into this, I would get 0 over something. And 0 over anything, other than 0 over 0, is 0. So an x value of 4, the derivative is 0 there, which means there is a horizontal tangent there. Now it says determine the coordinates of each point, and key thing here, coordinates, meaning we need the y-coordinate. If I want the y-coordinate of the point on the function, I now have to plug that value of 4 into the original function. So I need to figure out what is the value of h of 4. If I plug 4 into this function, I would get 2 times 4, that's 8, plus 8 is 16, over the square root of 4, which is 2. So 16 over 2, that's 8. So the point is the point 4, 8. Let's just verify that in Desmos. Yep, it was the point 4, 8. So if we wanted to write a nice sentence answer, we would say there's a horizontal tangent at the point 4, 8. All right, that's it for that lesson. Make sure you try the practice questions.